3, 2, 1. Alright, let's go. Alright, so what's the plan for today? Today we're gonna take a look at the exciting world of second-order linear homogeneous equations again. So remember, this is what they look like and what their solutions look like. Right, it is a linear combination of a fundamental set of solutions, and again that means that y1 and y2 solve the differential equation. So if I were to plug y1 into this equation right here, I will get 0. Same thing for y2. And the fundamental part, meaning that y1 and y2 are linearly independent functions. Right, and again, that means that scaling them up and adding them is not trivial. That produces a truly new function. There's no linear redundancy between the two functions. Alright, so we have solved a specific scenario out of these, specifically where a2, a1, and a0 are constants. Right, and as we noted, the differential equation, we can transpose it into a polynomial, and so solving the differential equation turns into finding the roots of a polynomial. Alright. Now, as we've noted, for variable coefficients, actually finding y1 and y2 is not necessarily an easy task. Outside of some, and with some quotes around that, nice cases. So today we're going to look at one such case. So specifically, equations that look like this are called Cauchy-Euler equations. They're also known as equidimensional equations, is another name I've seen for these. So, of course, our boy Euler showing up again. But here's a new name for you, probably a name you haven't seen before in mathematics. Augustin Cauchy, a French mathematician. One of my absolute favorite mathematicians. He is responsible for a lot of great mathematics. If Euler was the king of mathematics in the 1700s, then Cauchy probably was at least one of the top dudes in the 1800s, if not the guy in the 1800s. Speaking of kings, so Cauchy's French, and he lived in France, obviously, and man, he really liked kings. And this was a time in France where that wasn't popular. So as fundamental and as important as Cauchy's work was for mathematics, and not only just math, but engineering, so in your future career you might run into some stuff that he, specifically elasticity, has a bunch of stuff named after him. For as great as he was not popular, to say the least. His fellow mathematicians thought he was like a crazy jerk, basically. He didn't get killed in the French Revolution. He just left France for a little bit. They let him back in, and basically everyone was like, "It's all right. He's cool. He really likes kings." But so there's some fun quotes about Cauchy being a cranky man about that stuff. But anyway. So one thing that Cauchy did, that's what we're going to talk about today. So here is a second-order linear homogeneous equation. Now note it's a variable second-order linear differential equation. Here a, b, and c are constants, and here are the coefficients, right, are variable. Again, it's linear, even though, right, there's a multiplication technically happening here. You should think of it more as it's a scaling with respect to the independent variable. Okay. So, solving these equations, it turns out, is very similar to solving constant coefficient equations. Right? Because if we look at this and read it, right, and again, this is the very important skill, very key skill in differential equations. If we just read what this is saying, I need a function so that when I scale it, and then I add that to its derivative times x, that's been scaled, plus its second derivative times x squared times a, and once I add all of that up, that needs to equal 0. So y and its derivatives probably need to have something to do with x here, right? Because we're going to multiply by x's and add everything up. So probably a good idea to guess that x to the m would work, right? And once you take some derivatives and plug it in, you'll see that. But there's something that needs to be stated here before we do that. This is a minor point. Like I said, when it comes to domains of solutions to differential equations, the domain of a solution can be very different than the domain of the actual function. So in this case, we'll make our lives just super easy and go x needs to be a strictly positive real number. For negative real numbers, powers aren't a problem because, well, we now know what complex numbers are. 0 is also not problematic, but for negative exponents, it's an issue. So we'll just ignore that case. And for negative numbers, it gets dicey, so we're not going to worry about that. Keeping to the case of strictly positive, then raising it to any power doesn't, we're good. And that shouldn't be too surprising too, because again, look, the derivative and its second derivative are being multiplied by x. So if x is equal to 0, the derivatives vanish from the equation. It gets problematic. And right, that gets into something I've talked before, which are called singular points. And there's a whole, like, you could spend your entire life studying that. So we're not going to get into there. But there are some things to be said here. I mean, it's worth noting this because in a little, when we go about solving them, the techniques we use are actually going to require this strict positivity. But anyway, right, so like I said, there's these occasional moments where we gotta talk about domain for a second because it's going to have some implications on solution methods. But anyway, so let's go ahead and plug it into the DE, and note that the second derivative and the first derivative, well, each derivative will take 1 away from the power. And since we're multiplying by x and x squared, that undoes the -1, it undoes the -2, and so, hey, looky here, a polynomial times something has to equal 0. This has to be good for all strictly positive x. The only way that happens is if this piece right here is equal to 0. So the Cauchy-Euler equation, just like constant coefficient equations, have a polynomial that we can associate with them. So for Cauchy-Euler equation, sometimes it's called the auxiliary equation for the Cauchy-Euler equation. We're going to call it the characteristic, so we kind of don't confuse the two different equations. So now note this one is very similar, but has a serious difference that the m term is not just b, but it's b minus a. It's the only difference. It's a very minor difference, but it is it's there, so we need to keep that in mind. So here again we see solving a second order differential equation. You can turn it into just finding the roots of a polynomial, right? Like I said, there is a non-trivial overlap between polynomials and differential equations, and here we see it again. Okay, that's nice. That's really neat, too, when we kind of think about it, that we're basically overcoming a problem that has, this calculus sort of component to it, these differential, right, I had to figure out this derivative stuff, and we're defeating it purely algebraically. That's really neat. That's kind of cool. Alright, so that being said, now that we know that every Cauchy-Euler equation turns into just, here's a quadratic, get the roots, well, we've been here before. Alright, I've seen this one. It's a classic. So what's going to happen? Well, distinct roots, repeated root, and complex ones. So let's do them. Here you go. Here's the Cauchy-Euler equation. Let's go to its characteristic equation. Now again, it's basically the exact same thing. Replace the xy, xy, xy with m to the appropriate power. Here it's squared, here it's 1, no power, no m. The only thing that you need to keep in mind is that the m term is not just b, but it's b minus 1, and that's just how it turns out, Okay, so we get that, and oh boy, it factors nicely. We get two roots, so we've got two solutions: x to the -3, and x squared. And again, worth stressing that we are implicitly assuming x is strictly positive, so this is completely fine right here. Although this is defined for all other real numbers besides 0, we need the domain of a solution to a differential equation to be an interval. So again, not terribly important, but worthwhile to keep in your head. So we've got two solutions, so what do we need to do? Well, gotta check that they're linearly independent, and hey, their Wronskian is non-zero. They're linearly independent. That's a fundamental set of solutions. General solution to the DE. That's it. And I'm not joking when I say that that's it. That's really all we're going to kind of see today is that, hey, these get solved basically the same way. It's just a different auxiliary equation and a different guess that's helping us out. All right. So in the distinct real roots case, that's exactly what you think. If you've got two distinct real roots, they will form a fundamental set. So for a quick example, 2x squared y double prime plus xy prime equaling 0. The solution there will be c1 plus c2 square root of x, because the roots of the characteristic equation are 0 and 1/2. And that's it. Like they're right. There's no mystery to today. This is a comfy day. This is just like, oh, I've seen this before. It's just a little bit different. There's a little extra ins and outs. Okay, so as we saw with constant coefficient, the distinct real root case is kind of like the boring one. This is the one where it's like, oh yeah, everything just works fine. So the more interesting ones, of course, are repeated and complex. So let's talk repeated. All right. So in this case, the repeated root is a -2. I'm just, again, stressing that the coefficient on m is b minus 1, right? That's really the only thing. This is like the one little like a pitfall. Right? This is the rookie mistake here is just leaving this as 5. But you know, we're better than that. We're good. We're not just starting out here, right? So yeah. All right. Well, we got one solution. Y equals y1 is x to the -2. So hey, second order DE, I have a solution. I know how to find another one. I can use reduction of order. Now, the thing I need to remember about reduction of order, it's been a while. The thing I need to remember is that I need my DE to be in standard form, which means I need to divide out this leading coefficient. Okay, so we need to get the DE in its standard form. Now, again, remember, when we do this, this may introduce some weirdness with domain, but it's okay because, like we said, x is always strictly positive, so dividing out by it's not going to introduce any sort of, the weirdness. But we're good otherwise, but again, worth stressing. All right, so now that it's in standard form, there's a formula we could pop in. There's also the method of that y2 needs to be a function times x through the -2. You could solve it that way by plugging it in and directly computing. But there's a formula that always works. Here it is. There's some bad symbols there. There was like a comma that was a period earlier on. I didn't care. But that too looks dumb. Let me fix that. Yeah. I mean, like I said, this is a comfy day. I'm laid back. Normally, I get all like, like I swear to Jesus, this is not, But yeah, I'm good. I'm just let it roll off my back. I don't care. I don't care. I care immensely. Take a little water break. Yeah, I got water with me today. I don't have my Dr. Pep. But all right. Anyway, so hey, the second solution is just the first one times log of x. So for repeated roots in the constant coefficient case, we saw that it always boiled down to, well, you just multiply whatever you have by x. Here we see we multiply by log of x, and so naturally we want to ask, well, is this the only thing that happens? Or is there some other weird function that shows up? Well, the spoilers to that, and I don't even have a pause on this one. All right, well, yeah, I don't care. Right, so it turns out that you'll always multiply by log of x, and here's some examples for you. Yeah. I'm parched. I got a little. We're all a little sick in my house. We all got like a my wife got like a sinus infection, and yeah, we've all been a little scratchy in the throat. But anyway, so yeah, for repeated roots in the Cauchy-Euler case, right, the repeated root gives us the one solution next to the m, and then the other one you just multiply by log of x. So again, we're seeing it behaving basically just like the constant coefficient case. So we have a lot of parallels here, just some minor differences. Okay. So we've got one more thing to talk about before we call it a day, and that is, of course, complex roots. Now, before we get there, before we do that, let's take a moment and, take a breath, make a plan, and do our best. We're going to look at x to the m. X is a strictly positive real number. Now, the roots, then, if they're complex, we're looking at a real number raised to a complex power. So how are we going to handle that? So let's take a moment and attack that before we actually go ahead about solving a DE. All right, so remember, for real numbers, a and b, or a is strictly positive, a to the b, of course, is defined. You could talk about, 2 to the pi power, or, e to the pi power, or something like that. But all exponents are really e in disguise, thanks to e and the natural log interacting with each other quite nicely. Specifically, log of a, b times log of a is log of a to the b, and e and natural log undo each other. So any exponent can be written in terms of e and logs. And hey, e raised to a complex number, well, I know what that's equal to. So for any real number, a, strictly positive, and a complex number z, then a to the z we can just simply define as e to the z log a. Right? And this is totally fine. E to a complex number is a known quantity. We have access to that. And there we go. Sweet. Now, before we go forward, it is worth noting that for a non-zero complex number, we could talk about z to the w. So a complex number raised to a complex power is possible. It starts getting really bizarre, though. You start getting some really strange behavior. So, for example, I to the I is a really weird thing. So it turns out that depending on how you look at I to the I, it actually could be a real number. Specifically, I to the I is e to the negative pi over 2, if I remember right. I might be lying. No, that's not. Yeah, no, that's right. Yep, that's right. But it gets really weird. Because I to the I technically has other values. So complex number to complex power. You have to get into this theory of like multi-valued functions, and it starts getting really. That opens up a can of worms that I don't feel like getting into. But if that sounds really interesting, well, you should take Math 365, which is always offered in the spring. That I occasionally teach. It's a fun class. I like that one. DiffyQ, though, is my jam. I love this stuff. All right, but anyway, so for a quick example, speaking of fun numbers, pi to the I power then would be e to the I log of pi, and, well, e to the ix, I know what that's equal to. There we go. Euler's formula jumps in, helps us out, and we get that. So pi to the I is cosine of log pi plus I times sine of log pi, because, why not? And in general, we can get a pretty basic formula. If you look at x to the a plus bi, where a and b are real numbers, it breaks up like that. So there we go. All right, so now we've got a pretty good control over complex powers. So let's actually attack a problem where they show up. All right, now, like I said, this is my favorite class to teach. I love this stuff. And what I really love, too, is this problem. This is one of my favorite problems. I've got a lot of problems in this class that I just, love. This one, though, this one's near and dear to me. Near and dear to me because I was born on September 17th. And, hey, this has got complex roots. I had a good chuckle when I discovered this one. I think I saw it as an example in a textbook, and I was like, "Oh yeah, that's funny." I didn't narcissistically let me plug in 917 and, you know, make that, see what that goes there. But anyway, so, yep, so now you know my birthday, so do what you want with that information, I guess. So side note, there's a professor in the math department, we almost have half birthdays. The half birthday for this would be March 17th, and this person was born February 17th. And we were very disappointed that it was off by a month. We were like, oh, that's lame. But anyway, fun fact though. Speaking of half birthdays, our daughter's birthday is her half birthday is me and my wife's wedding anniversary. So that was a nice little, that was fun. Anyway, all right. So we got complex roots. So that means, well, we can get technically two solutions. And well, we know what's going on here. We've seen this before. Well, the solutions that I get involve complex numbers, but the problem I started with had no complex numbers, so I got to do something to get rid of them. Now, sine and cosine are even and odd, so we get this. Shouldn't be too surprising because -4 plus I, -4 minus I are conjugate pairs, right? The conjugate of this is that. So this number is the conjugate of that one, is also not too surprising. And because of that, we can superposition to isolate the real part and the imaginary part. And you get this, so very similar to what we saw with complex roots in the constant coefficient case. Now, what do we have to do? Now that we have two solutions that are real, well, I need to make sure that they're linearly independent, and if you're looking at this and you're cringing, going, oh god, I have to take the derivative of this, which means I have a product rule that's going to cause a chain rule, I agree. I went ahead and just plugged this into Wolfram Alpha and went like, what's the Wronskian of this? And it's like, oh, it's x to the -9? Oh, that isn't too bad. That shouldn't be too surprising that it happens. If you think about the derivatives here, right, a 1 over x is going to spit out, right, we're going to get a cosine squared log and a sine squared log, so they're going to delete each other. So it shouldn't be too wildly surprising that the Wronskian here actually cleans up very nicely. But if you didn't feel like taking the derivatives, you could just, I don't know, sometimes, just put in the Wolfram Alpha and see what it says. Don't call me out on that one. Professor Butler, I watched him give a talk once about something, and he had some awful formula that he had to simplify, and he was like, well, I put in the Wolfram Alpha and it spit out this simpler formula, and then I proved that the simpler formula was right, but, I didn't actually prove that the Wronskian is this, but it should be. But anyway, and then boom, there we go. We got a nice general solution to the DE, and in fact, this is what always happens if you have complex roots, alpha plus I beta. Then the general solution will always work out in that form. That should look incredibly familiar because this is very, very similar to how constant coefficients went. So for a parting shot, here's an example. The complex roots there are 2 plus or minus 3i, and then there's the solution. Okay, so, hey, there we go. Variable coefficient, second order, homogeneous, differential equation, linear, solved. How could we make variable coefficient problems worse? Well, I guess we'll see you next time.